In the last video, we talked about communication between the threads using the shared state approach. In today's video, we're going to talk about the second popular approach, which is message passing. Under this approach, we have 6 patterns. We'll discuss about each pattern and the underlying primitive in detail. And along with the code, I'm also going to give you a visual demonstration of each pattern so that you have a clear understanding of how each pattern works. So without any further ado, let's get started. Before we look into the examples, let's set up a few things. I'm going to use the same project code base that I used in the last 2 videos. So I updated the UML file with the message passing section where I listed the primitives and also the patterns that we'll cover in this video. And I created a new folder called message passing. Inside that, I'm going to create different demos and expose them through the mod file. And in the main.rs file, I'm going to import this module and run the examples like this. That's it. Let's look at the first pattern, which is a single producer and a single consumer. And first, let's create this in a single thread. And whenever you create a channel, you get a sender and a receiver. And the sender can send the messages through the channel to the receiver. Let's implement this demo. First, we're going to look at a very basic example. So first, we're going to import the MPSC primitive, which stands for multiple producer single consumer. Then we can create the channel by calling the channel function inside this module. And this gives you a transmitter and a receiver in the form of a tuple, and we can destruct the tuple like this. Then we're going to send the first message through the transmitter, and then we can use a while loop to continually listen to the receiver messages. And finally, once the receiver is closed, we can print that all the channels are closed. Let's save this. Let's run it. Awesome, we did receive the first message through the channel, but you can see that this channel never closes, right? We don't exit this while loop. That's because we need to understand when this channel closes. So only when the transmitter goes out of scope, this rx.receive will throw an error, which is when it exits out this while loop and gets to the statement. To understand this, we need to implement multi-threaded channel. So let's go ahead and implement that. To create a channel with threads, first I'm going to import the spawn function from the thread module, and then I'm going to wrap the tx.send part of the functionality inside the spawn function. That's it. Now let's run this. Now we can see that the receiver did receive the message, and then we exit the while loop and we get the last print line statement as well. So how does this work? How do we gracefully exit this loop? This is how it works. Whenever the transmitter exits the scope brackets, it goes out of scope and it gets dropped, which is what makes the while loop, the dot receive function error out and exit this while loop, and that is how we get to the next line. So here is a rule of thumb. Whenever the transmitter goes out of scope, it automatically gets deallocated, which is what we gracefully handle in this receive function and this while loop, and which is what we use to exit out the while loop and go to the next line of execution. The next thing to understand is the sequence of messages. In this case, we are only sending a single message from the transmitter to receiver. But what if we need to send multiple messages, right? What will be the order of the messages? So instead of sending a single message, let's create a loop. So I replaced the single send message with a for loop that will send 10 messages. And let's see what the sequence will be. As you can see, the messages did receive in the right order. So this obeys a FIFO order. FIFO as in first in, first out. The next thing to pay attention is, can we send the data? Can the receiver borrow the data instead of sending it from the transmitter? And the answer is no. The way this works is you are moving the data from the transmitter to the sender. So as soon as the receiver receives the data, that becomes the owner of the data from a Rust borrow checker standpoint. So yeah, the data is moved, and the borrow checker principles, they still apply, but you can't send a mutable reference or an immutable reference to the receiver. Here is how it visually looks. In the last example, both the transmitter and the receiver lived on the main thread, but here we have created a new thread for the transmitter while the receiver is still on the main thread. And when we send multiple messages, they obey first in, first out order. In this section, let's see how do we send different kinds of data. So by default, when you create a channel, you can see that the sender and receiver is of type string, but this function, it is a generic function and it can take a generic type. So when you create a channel, by default, it creates a channel of type string, and this is how we pass the generic type. So instead of a string, let's send U32 values, and this is how it works. So instead of string, you pass the generic type as U32, and as soon as you do that, you will get an error that of mismatch of types in the sender. So instead of format, I'm directly going to send I, which is of type U32, and now the error goes away. Let's run this. Awesome. So instead of sending strings, you could now send U32, and you also see the sender and receiver as type U32. Okay. Not just primitive types like string, U32 or floats, you can also send compound types like struct. So let's create a struct and pass it through the channel. So I created a struct called mango, and it has two fields, layer and color, which is a U32 and a string. And I can change the channel type from U32 to mango, and as soon as we do that, we get this error of mismatch types. So I created this data variable that holds the mango, and we send it through the transmitter, and we can see that the mango doesn't implement the display trait. That's an easy fix. All you have to do is implement the debug macro on the struct, and then instead of directly displaying the message, we need to do a colon and question mark and then pass the message. That's it. Let's hit save. Now the error disappeared. Let's run this again. Awesome. So this is how you can send a complex data type. In this section, let's look at the second pattern, which is multiple producer with a single consumer. And before we implement that, let's do some cleanup. I want you to have the previous example with a simple channel instead of a compound struct type. So I cloned this and restored the previous example in this module, and I also exported that in the mod file. And let's clone this one and create a new file called multiple producer and single consumer. That's it. Now let's export this in the mod file. That's it. Now in the main file, instead of running the single producer example, let's run the multiple producer, the one that we just created. All right, that's it. Let's update this example to send data from multiple threads. So instead of having the for loop, I'm going to move the for loop to outside the thread. And as soon as I hit save, I'm going to change the value from 1 to 10 to 1 to 3 so that I can only spin 3 threads. And when you hit save, you will get an error that the TX value has already moved. So the reason this is happening is because when you run the for loop, on the first iteration, the ownership of TX is already sent to the child thread. So it doesn't let you access TX in the subsequent threads. And the way you can resolve this is by using the clone function on the transmitter. So clone lets you clone the transmitter and pass it to the child threads without having to break the borrow checker rules of Rust compiler. As per the documentation, clone is considered as a cheap operation, and you can feel free to create any number of clones. Okay. So I created a new variable called txclone, and instead of tx.send inside the thread, I'm going to say tx_clone.send inside the thread. And now when I save it, you can see that the error has disappeared. I'm also going to change the message to make it appropriate. So instead of message I from the sender, I'm going to say thread I message. I'm going to remove from the sender. Let's hit save, and if we run it again, awesome. We should see that 3 messages are sent from different threads. Okay. Even though you're calling spawn in a particular order, the order in which the threads are spawned is not guaranteed. So that is why you see a different order for each thread. But keep in mind, inside the thread, all the messages that you send will still follow the FIFO sequence. Okay. And another thing that you notice is that we never exit this while loop, and we never get to the print line statement. So one thing you can do here is after the for loop, you can drop the transmitter. And now if you run this again, awesome. We should see that the while loop breaks and we move to the next line of execution. Perfect. This is how you handle closing of the channel, and once the task that you want to perform through channel, once this is completed, this is how you handle it and move on to the next functionality within your code base. From a visualization standpoint, this is how a multiple producer and a single consumer setup looks like. We can see that the producer are sending messages through the channel to the consumer. One issue with this setup is that when you have a slow consumer that is processing messages slowly, the messages could pile up because this is an unbounded memory setup. The regular channel is of unbounded memory setup, and that could create a bottleneck. So let's see how that happens. So I created two logs inside the thread, one before sending the message and one after that, and let's see what happens when we run it. You can see that the messages 3 and 1 are sent, and then the receiver receives the message. The point that I want to convey is not exactly apparent. What I want to show is, as soon as the messages are sent immediately, and they don't wait for the consumer to process. So what that could happen is it could lead to an unbounded memory situation where you have a lot of unprocessed data that is still holding in the buffer, which can create a bottleneck. So what I'll do is, inside each thread, I'm going to create a for loop. So I created a for loop inside each thread where I'm going to be sending 10 messages instead of a single message. And I also updated the print line statements to account for that. And let's see what happens when we run this. As you can see, the messages are sent immediately, and the program doesn't wait for the consumer to receive the messages. So if you scroll down, you can see the receiving starts from here, and by this time you can see all the messages are sent. So this could create a bottleneck. Here is how this issue looks visually. You can see that the producers are sending multiple messages at once, which are immediately sent to the channel, and they just stay there until they are processed, which could create a bottleneck. The solution for this is to use a synchronous channel instead of a regular channel, where the consumer has control on the frequency at which the data is sent. And that is what we're going to cover in the next pattern. Okay. Before we discuss bounded channels, let's do some cleanup. I marked the previous pattern as complete, and I also duplicated the multiple producer module and renamed it to bounded channels and exported this from the mod file. And in the main file, we're going to run this example instead of multiple channels. Okay. And this is how you define a synchronous channel. Instead of channel, you just call the sync channel function. And this function takes in a parameter which is the buffer length. And I'm going to set the value to 1. For now, we'll set it to 1 to clearly show you how this works. So this buffer length decides how many messages can stay in the transient phase before they are processed by the consumer. That way, the producer cannot just send all the messages at once. It can only keep a maximum of 1 message in the transient phase before they are processed by the consumer. Okay. To show the differentiation, I'm going to change it back to channel and remove the parameter. And I also added a 2-second sleep after all the producers are spawned and messages are sent, just to show you that all the messages are sent immediately. So if I run this, you can see all the messages are sent right away. 3 threads and 10 messages from each thread, they're sent right away. And after 2 seconds, you can see all the messages are processed immediately. So there is no buffer or transient length defined. So if you change it back to sync channel and set the length as 1, and let's see what happens now. Before we run it, I also want to add a small 1-second timer inside the receiver so that each message takes 1 second to process, so that you can clearly see that the messages are not sent all at once, and at any given point a maximum of only 1 message will stay in the queue. Okay, let's run this. Alright, you can see only after the message is received and processed, the producer was able to send the next message. Okay, so that's how a bounded channel works. All the other features of a regular channel are still applicable to a sync channel, like sending the messages in a FIFO order inside the thread, and also being able to pass different types. The sync channel is also a generic function like the regular channel, so you can pass the type by passing the generic type. Instead of a string, you can use a struct or enum or any other primitive types. Here is how a synchronous channel looks visually. At any given point, not more than 3 messages stay in the queue. until the message is finished processing, and then the producers can continue sending the message. And you can define any length. For now, in our example, we only have a queue length of 1, but we can set it to 10, 5, or whatever we want. This acts like a padding and prevents the buffer from overflowing. Okay. In this section, let's look at controlled cancellation pattern. But before that, let's mark the previous one as complete and also create the new module. Alright, I flagged the previous chapter as complete and created a new module called controlled cancellation. Export that in the mod file, and I'm also running that example in the main.rs file. In this example, we're going to implement a regular channel, but instead of automatically closing the channel when the transmitter goes out of scope, we are going to control the status of the channel using the payload. Okay, and we can achieve that by creating an enum, and inside that enum we can segregate our messages as work or based on different statuses. And whenever you send a payload with a certain status, that is considered by the receiver as a signal to close the channel. So let's implement that. First, I'm going to import all the required dependencies, which is MPSC module to create the channel, and the thread to spawn the threads, and also duration to implement some kind of timeout. Okay. Then I'm going to create an enum called command, and we're going to have two different kinds of payloads. One is work with a U32 value, and the other one is stop, which is when we considered as a signal to close the channel. Okay. Then I'm going to create a simple regular channel, and this is how we can pass the generic type as command, and that gives you a tuple of receiver and transmitter. Okay. And then I'm going to create a for loop and send the work type payload 3 times, and after that I'm going to send the stop payload to close the channel, and finally we can drop the transmitter, and then we can create worker threads for each receiver. And inside the thread, so we're going to match the command and handle the different types. So if it's a work type, we're going to make the thread sleep for 30 seconds to give the illusion of the worker performing some task, and if the value is stop, we're going to break the loop, which is going to end the receiver. Awesome. So the receiver did handle the first 3 messages, and finally when it received the stop signal, the channel got terminated. You must be wondering, what if the stop payload is received before the work payload? In that case, wouldn't it result in an abnormal termination of channel? That is not the case, because all the messages that we send within a single thread are sent in a FIFO fashion, right? First in, first out, which is why the receiver would receive the stop signal only after all the work signals are received. That guarantees that the channel is not prematurely terminated. So this is how you can control the termination of channel using a command, using an enum type. Okay. The beauty of this pattern is, if you need to send multiple types of data, you can create an enum and segregate different types. Just like work, what if you need to have status or some other type, you can just define all the types and use the match operator to handle different types of payloads. Okay. Here is how the visualization looks when we send the work payload for the first 3 times. That is processed by the receiver, and as soon as we send the stop payload, the channel gets terminated. In this section, let's look at one-shot request response, but as always, I'm going to mark the previous chapter as complete and create the new module. Alright, now that it's done, let's go ahead and implement this example. A one-shot request response is a pattern where a channel takes in a message and immediately sends back a single response. So the key thing to note here is that the channel will only send a single response during its lifetime. So it works pretty much like an REST API, where when you call an API, you immediately get a response back and the connection doesn't exist anymore. So it's like a one-time interaction between the sender and the receiver. So let's go ahead and implement this. First, I'm going to import the required modules, and we're going to use a regular channel to implement this. First, I'm going to create a channel, and this is going to take in a generic type of a tuple, which contains the first value as the U32 type, and the second one is of the sender type. The way this works is we're going to have a main channel and also 3 child channels, and these child channels are going to have the one-shot request response implemented, and we're going to calculate square of a number. And the way we're going to do it is, the receiver of the main channel is the one that's going to do the computation, and the way we'll do it is, when we send the data to the main channel, we're going to send the value as well as the transmitter of the child channel. And once the square is calculated, we're going to send the response back to the receiver of the child channel using this sender. And this might look like a mouthful, but trust me, once we implement the code and I'll show you the visualization, everything will be clear. So let's go ahead and finish this implementation. So now that we have the master, the main transmitter and receiver, I'm going to create a worker thread, and inside the worker thread I'm going to implement the receiver of the main channel. Okay, and this is what's going to do the computation. So we're going to have a for loop, and it is going to loop through the input and the child transmitter, because like I said, this main channel is of generic type, which takes a tuple of the number and the sender, right? And then whenever a message is sent, we're going to calculate the square and format it, and then send it back to the child receiver using the child transmitter. That's it. Let's go ahead and implement the child channels. So we're going to have a loop that runs 3 times, and inside each loop I'm going to create a channel. These are the child channels, and I'm going to send the number, which is the index of the for loop, and also the child transmitter, and I'm going to wait for the response. And because one shot response only contains a single response back from the channel, we only need to call the .receive function once. Finally, we just print the response and we drop the main transmitter, and finally we just call the join function to make the main thread wait for all the channels to be closed. That's it. Let's run this. Awesome. So we got 3 responses back, each containing the square of the number that we passed. Here is how the visualization looks like. We have first the main transmitter and the receiver, and then we'll create 3 child channels, and for each channel we're going to send both the number that we want to square along with the sender, and the main receiver is going to calculate the square and send the response back to the child receiver using the child sender. In this chapter, let's talk about pipeline with stages, but before that, as always, I'm going to mark the previous chapter as complete and create the new module. Alright, it's done, and I also created a new module for pipeline stages. Pipeline with stages is a pattern that is useful if you have a work that can be clearly delineated into different tasks and you want to parallelize each task individually. So if you want to transform data through well-defined sequential steps, this is a pattern that can be useful. To demonstrate pipeline with stages, we're going to create 3 channels, and within each channel we're going to transform the data. So I'm going to give you a mock example of transforming potatoes into French fries. So in the first stage, we're going to transform potatoes into wedges, and in step 2 we transform wedges to fries. So let's go ahead and implement that. So let's go ahead and implement this. First, I'm going to create 3 channels, and to keep it simple, I'm going to name the transmitters and receivers in the right sequence. Okay. And in stage 1, I'm going to add a receiver for the first channel inside a separate thread, where I'm going to listen to all the incoming values and transform potatoes into wedges. Okay. Similarly, in stage 2, I'm going to add a thread for where I'm going to listen to the second receiver, and I'm going to transform the wedges into fries. Okay. And finally, I'm going to add a loop where I'm going to send 3 batches of potatoes, and I'm going to add a listener to the third receiver where I'm just going to display the final value. And finally, we can just join the 2 threads to make sure the main thread waits until all the threads are closed. Let's run this. Awesome. So I added this pipe symbol as the delineator between each step. So you can clearly see the potatoes batch 1 being transformed to wedges and finally transformed into French fries. But one thing that you notice is that the program doesn't end. It is still running because the channels are not closed. Now, because we have 3 channels defined on the main thread, you might be thinking that we need to drop all the 3 transmitters, right? But that is not the case. Just by closing the first transmitter, just by dropping the first transmitter, that should automatically drop all the other transmitters. So let's run this and see this in action. Awesome. Now you can see that after all the potatoes are transformed to French fries, the program ends. Can you explain why we only need to drop the first transmitter and not the other ones? Just think about it. I'll explain shortly. Alright, so here is how this works. Notice that we have two threads here, one for receiver 2 and one for receiver 3. And inside the thread, we are using TX2 on the first thread and TX3 on the second thread. So whenever you spawn these two threads, the ownership of TX2 and TX3 are automatically moved to the child threads. Okay. Now, what happens when we drop TX1? When we drop TX1, RX1 would automatically know that TX1 is dropped, and that should end this for loop, right? And once this for loop is end, the child thread gets closed. So as soon as the child thread gets closed, TX2, whose ownership is transferred to the child thread, will automatically go out of scope, and that would close RX2. Same thing for TX3, because it is moved to the child thread. Once that gets closed, RX3 would also get closed. So that is how it creates a cascading effect, and once you drop TX1, all the other channels will automatically get closed. Here is how these three channels work in tandem. The first channel receives batches of potatoes, and they are transformed into wedges and sent as the input to the second channel. And the second channel takes these wedges and transform them into French fries and sent as input to the third channel. And on the third channel, we just print the final result. That's it. Before we wrap up the video, I want to mention a few things. All the channels that we implemented in today's video are part of MPSC, Multiple Producer Single Channel module, that is part of the standard crate. Now recently, a new multiple producer, multiple consumer channel is implemented in the standard crate, MPMC module, but it's still in experimental phase, which is the reason why I haven't covered in this video. But maybe in the future, this could change. So if you want to implement multiple consumer pattern, then this is something that you want to look out for. Apart from the standard crate, there is another crate called Crossbeam, which also provides different kinds of channels along with multiple consumer channel. But this crate is updated almost 2 years ago, which I feel is a little old, and some of the concepts could be obsolete. If you scroll down, you will find Crossbeam channel, which provides a multiple producer and multiple consumer channels for message passing. So this is something that you want to read. Even though you may not use the library directly, maybe some of the concepts explained in this module could be helpful, and they might be made available at some point in the future in the standard library. With that, we'll end this video, and let me know in the comment section if you have any thoughts or suggestions, and I'll talk to you in the next one. Bye.